Sayan is an associate professor at the University of Warwick in England. And he has many results, and he will talk about one of them in dynamic graph algorithms. Today he will talk about more generalized results on packing and covering it. Looking forward to your talk.
Thank you, Monica. So basically, in the last 2 days, David, Aaron, and Sohail, all three of them gave great talks related to dynamic matching. So my talk was also supposed to be on dynamic matching, and then I thought that there would be too much of dynamic matching in one workshop. So I changed it to dynamic packing covering LP, which is basically generalization of dynamic matching. So this is joint work with Thachapal and my student Peter. Let me start with the introduction. So I'll just start with a brief story about Richard Feynman. I don't know if the story is historically accurate, but that's besides the point. So what was Feynman's favorite method for problem solving? It goes like this. It consists of 3 steps. Step 1, write down the problem. Step 2, think very hard. And then step 3, write down the answer. Now, this seems very generic. If we just ask for a specific context, let's say for designing static approximation algorithms for computational problems, what would be a more specific version of this method? Well, it so happens that for a non-trivial fraction of approximation algorithms question, it would go like this. Step 1, write down a suitable LP relaxation. Step 2, think very hard. And step 3, write down a good rounding scheme. Now, as you can see, if you just look up any standard textbook on approximation algorithms, there will be several chapters just devoted to this framework. There are examples of this. So for instance, yesterday David's talk was on this topic, but most of this framework until now has been mostly applied for dynamic matching and set cover. And if we ask why is it that there are relatively fewer instances of dynamic rounding schemes? I think one answer would be that it brings in new kinds of challenges. So if we now look at time complexity in the standard approximation algorithms literature, for step 1, solving a suitable LP relaxation, and step 3, implement a good rounding scheme, we are just happy with polynomial running times. However, for most dynamic problems, we would ideally like to get polylogarithmic time for both these 2 steps. And this is a new challenge that we need to deal with. And in both these 2 settings, for step 2, you have as much time as you want. Okay, so what are our contributions? Our main contribution is for a large class of LPs, packing covering LPs, we resolve the complexity of maintaining approximate solutions to them in the dynamic setting. And as you might know, bipartite matching and set covers are special cases of packing covering LPs, but there are many other instances that are captured, many other problems that are captured by packing covering LPs. And at a high level, it just says that we are reducing the question of solving dynamic packing covering problems to the question of designing good rounding schemes, because we can maintain the fractional solutions fast. And to do this, basically, we initiate a systematic study of the multiplicative weights update method in the dynamic setting. Okay, so what are our main results? Let me precisely define packing covering LPs first. So after doing some very standard scaling, which I will just ignore, the problem looks like this. We are given a constraint matrix C. All the entries in this matrix are non-negative. And the covering LP problem asks us to find a vector x whose L1 norm is just 1. So sum of all the coordinates of x is 1. And it satisfies these covering constraints that c times x is at least 1. And for the dual packing LP, we want to find a vector y such that c transpose times y is at most 1. And again, the sum of the coordinates of y is equal to 1. Now, in this talk, I'll be mostly focused on epsilon approximate solutions. And by that, I just mean for a covering LP, just find a vector x, which basically satisfies these covering constraints up to a multiplicative factor of 1 minus epsilon. And similarly, for packing LPs, find a vector y, which satisfies these packing constraints up to a multiplicative factor of 1 plus epsilon. Now, what is the dynamic packing covering LP problem? Well, in the fully dynamic setting, you can naturally ask that an update is basically changing the value of some entry in this constraint matrix. And what will be partially dynamic settings? You can think of two settings which mimics sort of like incremental and decremental algorithms for graph problems. You can talk about restricting updates and relaxing updates. And restricting updates basically means that the feasible region of the LP just shrinks. Relaxing update means that the set of feasible solutions only grows. So for instance, for a covering LP, a restricting update would decrease the value of some entry in this constraint matrix Cij. Because then if you reduce the value of Cij here, maybe a solution that was already feasible before is no longer feasible. Okay. Now, I just said this. You can think of other natural types of updates in the partially dynamic setting, like just insertions of constraints and so on. We can handle those as well. But just as a reference point for simplicity in the talk, I'll just focus primarily on entry updates. So with this setup, what are our results? Our first main result is that we can maintain epsilon approximations to packing covering LP in partially dynamic setting in amortized polylog update time. And we complement this. So we obtain this using multiplicative weight updates. And we complement this with a strong lower bound, conditional lower bound based on SETH, which basically says that even getting polylog approximation is not possible in better than linear update time in the fully dynamic setting. So in the fully dynamic setting, essentially what you can do is just recompute the solution from scratch after every update. And the lower bound is a relatively straightforward reduction. So in the talk, I will just primarily focus on the upper bound, the result. Yes.
So you encode the, I guess, what would usually be the objective by the normalization constraint?
Yeah, exactly.
And that you can or cannot update? Like, I mean, I guess
that you can update. As I said, okay, that's a good question. Let me just go back to the formulation here. Let's say in the partially dynamic setting, or even in the fully dynamic setting, if you just look at the objective function, you can say that, okay, let me just update one coefficient in this objective function. That you can, and that would still be captured by this framework.
But would it have to go in a specific direction, I guess, like up or down?
Yeah, so in the partially dynamic setting, it will determine whether you are, it will be determined by whether you are thinking about a covering LP or packing LP vis-a-vis restricting or relaxing updates. But you can handle all those updates. Okay. Good. So rest of the talk, I'll just be focusing on this result. So what's the plan? I'll start with a basic algorithm in the static setting, forgetting all about data structures. Okay, just the vanilla static algorithm. Then I'll talk about how to just intuitively make it dynamic, why it should be easily dynamizable. Then I'll just come back to the static algorithm and talk about a slight modification which allows us to implement this in near linear time. And finally, I'll just show how to implement this in polylog update time in the partially dynamic setting. Now, one other thing I'd say is the basic static algorithm was already well known in the literature. So there are many people in the audience who have worked very extensively on multiplicative weight updates in the past. And our basic static algorithm is essentially, let's say, Gauss-Kohnemann algorithm, okay, the dual of that. However, I'm just going to give a fully self-contained presentation because I think the presentation still contains some nice insights. So for instance, we are giving a width-independent solver for packing covering LPs, and we are analyzing it in a black box manner by invoking the regret minimization bound for the experts problem, and which we could not find explicitly stated in the literature before. And it's also relatively simple. Okay, so I'll just start with the basic static algorithm. So for the purpose of these talks, I'll just use these notations. So I'll just think of packing covering LPs as generalizing set covers, and I'll just visualize the constraint matrix as just a bipartite graph. So the elements correspond to dual variables. There are m of them. The sets correspond to primal variables. There are n of them, and they are x1 to xn. And there is this complete bipartite graph. So the edge between element I and set j has this value Cij. And each of these values are bounded by 0 and lambda. They are at most lambda, where lambda is a parameter. Okay. And when we are looking at a primal covering LP, so what is happening is it's a covering constraint. So the covering constraint is on the elements. So we are just looking at all the edges incident on that element. For every such edge ij, its value gets multiplied by xij. And we are just saying that the total value of all the edges incident on this element needs to be at least 1 minus epsilon. And similarly, when we are looking at the dual packing LP, the constraints are on the sets, and these are packing constraints. So you're just saying the sum of the packing values of the edges incident on xj is at most 1 plus epsilon. So this is how I'll visualize it. Okay. And our goal is just this: either return an approximate covering solution or return an approximate packing solution. One of them. That's the problem. Good. So what's the basic static algorithm? Okay, it will consist of t rounds, where t is roughly lambda times log n divided by epsilon squared. And we will work with weights. So we will keep a weight for every set denoted by xj hat initialized to 1, and a weight for every element denoted by yi hat initialized to 0. And we will maintain primal solutions and dual solutions, which will just be the normalized weight. So henceforth, when I'm talking about the value of the variable xj, this is by definition the normalized weight of the set xj. And similarly, the value for the variable yi is just the normalized weight for element I.
Just to be pedantic, I mean, you're dividing by 0 if you're,
Good point. It will not be valid just after the first round. That's true. Okay. So all the time, we are just maintaining a primal solution whose L1 norm is 1, and a dual solution, a dual solution whose L1 norm is 1, and the primal solution whose L1 norm is also 1. We now just want to satisfy the constraints approximately. That's the setup. Okay. So now it runs in t rounds. What happens in a given round? At the start of this round, if x, our set cover solution, is already approximately feasible, nothing else to do. We just return x and we stop. Or it's not feasible. That means there must be some violated covering constraint for some element I. So I'm just highlighting the edges participating in this constraint in red. Okay. And now what it tells us is, to satisfy this, we just need to raise the weights on the corresponding sets. And we do two things. We first increase the weight of the element additively by 1. So we are increasing the dual weights additively. And we will increase the primal weights multiplicatively. So for every set xj, for every set j, what is this Cij divided by lambda? Is just this coefficient divided by lambda, so that this quantity becomes between 0 and 1. So if this set has Cij value large, we should raise its weight more, and so on. That's it. And now I will just refer to this operation as whacking this constraint I, because we are as if just trying to satisfy this constraint. So I'll just call it a whack. And that's the entire algorithm. And I'll just refer to it as whack-a-mole multiplicative weight updates, because you can just visualize these elements as being moles. And in each round, you are just identifying a mole, a constraint that is violated that you need to whack. And once you figure out that, okay, there are no more moles to whack, by default, you have an approximate covering solution, you return. That's the algorithm.
So for all j, is it for all j in the violated constraint?
Oh, here I'm just visualizing it as a complete bipartite graph. So these Cij's would be 0 if j does not appear in this constraint. Just for interpretation.
Yeah.
Okay. Now,
So the
Yeah.
one there should be 1 minus epsilon.
okay, good point. I'll just come back to it later on. In the static setting, this 1 is fine. In the dynamic setting, you'll need to make this 1 minus epsilon for a slight technical reason.
Sure, this whole approach requires writing the LP explicitly, right?
Very good point. It does not work for implicit LPs because our entire update times and run times is just in terms of the number of non-zeros in the constraint matrix explicitly. Okay. And I will just say one other thing, that if you just view what is happening to the packing LP this step, this is basically Gauss-Kohneman algorithm, if you are familiar. Okay. Now, how to analyze this? So the first thing to note is, if we return in this part, because we already found an approximately feasible covering solution, it's trivial to say that, okay, we have correctly solved our problem. Nothing to argue about. So the key lemma that we want to prove is that if we did not enter this step, then after capital T rounds, Y is actually an approximate feasible solution to the packing LP. And if we have that, then we are either always returning a valid covering solution or a valid packing solution. That's that.
Just another, at some point you mentioned width independent.
Yeah.
That's lambda, right?
Good. Right now, the analysis I'll give will depend on lambda, but later on there is an implementation where you can get rid of it. Okay. So now the proof of the key lemma. Here we will just invoke the experts setting as follows. We will just assume that each set corresponds to an expert, and we are in this following scenario. There are T rounds. Now, at the start of each round, we pick an expert according to the distribution X, because X is a distribution, because it has L1 norm 1. And now, nature, which actually is the algorithm, finds a violated covering constraint, because otherwise that round would not have run, I. And the payoffs of expert J would just be given by Cij divided by lambda, so that these payoffs are now between 0 and 1. And so we receive some expected payoff. What is our expected payoff? Okay, we pick expert J with probability Xj, we receive this payoff, sum over these things. That's our expected payoff. And after this, we basically update the weights on each expert multiplicatively. And you will notice that the way we are updating these weights, Cij divided by lambda, this is precisely the payoff that expert J receives. So this is precisely the expert's setting. Okay. Now, just applying a very well-known lemma. So what is our objective? Our objective is to basically maximize our payoff in comparison to the best possible expert in hindsight. So applying a very well-known lemma, we have this inequality. Here, even ignoring this equation, these symbols, all it is saying is this term is just the average payoff we get across over T rounds. This is sort of like our average regret. And all we are saying is that our average payoff is very close to the average payoff of any given expert J. And there is this multiplicative 1 minus epsilon term here. Now, what does this tell us? First of all, we are setting capital T to be large enough, precisely so that this average regret becomes small. So if we set t to be like this, our average regret just becomes epsilon over lambda. And that was the only reason why we set t to be like this. So after this substitution, this is the new inequality we have. And what I will do now is I'll just upper bound the average payoff we get and lower bound the average payoff of expert j. If you now look at the average payoff we get, what can we say? Fix any round t. Let I be the violated covering constraint at round t. So what is our average payoff? Just by definition, in round t, just look at those highlighted edges. That's the violated covering constraint. Expert j is being selected with probability x j. So this t just denotes that we are in round t. And its payoff is just Cij over lambda. And we chose a violated covering constraint in round t. That just means that the sum of these Cij values over all j is at most 1. That covering constraint was violated. So our expected payoff is at most 1 over lambda. So if our payoff in any given round is at most 1 over lambda, of course our average payoff over all rounds is still at most 1 over lambda. So now we can just know that our average payoff is at most 1 over lambda. This regret was at most epsilon over lambda. So we just add these two things up. The right hand side is just 1 plus epsilon divided by lambda. Okay. Now we will just lower bound the average payoff of any given expert j. And this will just tell us that the packing constraint on the set j is satisfied approximately. This is where this 1 plus epsilon term will come from. Okay. So what is the average payoff of expert j? Again, fix any round t. Let I be the violated covering constraint in round t. What is the payoff of j in round t? By definition, it's just Ci of j, this coefficient divided by lambda. And now we just observe that this is the reason why we additively increased the dual weight yi by 1 in that round. We observe that this term Cij times the dual weight, actually this increase is exactly equal to Cij, because yi hat we increased additively by 1. And in round t, we only increased the yi hat and no other weights on other dual elements. We only increased yi hat. So this increase is just the same as the increase in the value of the packing constraint, because for all other I primes, yi prime hat did not increase at all. Okay. Now, this side, this term is just the value of the packing constraint for j and the unscaled value with respect to the weights, unnormalized values. Now, what can we say? We initialized these packing weights to 0. So initially, this packing value was 0. And after every round, the packing value increased by exactly the same amount as the payoff received by that expert, modulo this 1 over lambda term. So at the end of all the rounds, the total payoff of expert j is just precisely 1 over lambda times the packing value of that constraint, the unscaled packing value. And so the average payoff of expert j is just this divided by the total number of rounds. And now what can we say about the total number of rounds t? It's just the sum of the dual weights. And why is it the case? Because in each round, after implementing the round, we just increased one of the yi hat values by 1. So if capital T, the number of rounds, is just the total value of all the dual weights, of course, yi prime, the actual dual value, the normalized dual value, is just yi prime hat divided by t. And if we just look at this expression, it just gives us that this is equal to 1 over lambda times just precisely the packing constraint value, the left-hand side. And we plug these two things together. What do we get? So this is the average payoff of expert J. I have just put this thing here. So just look at these two inequalities. This lambda will just get cancelled. You can take this 1 minus epsilon on the other side, and you will just see that the dual constraint corresponding to set J is satisfied up to a multiplicative 1 plus epsilon factor. And hence, this just implies that at the end of t rounds, Y is an approximately feasible solution to the packing LP. That's it. And I'll just say this, there is nothing new in this algorithm, but one thing that I myself find a bit interesting is that, as I said, if you look at what is happening to these yi values, that's precisely Garb-Konanman type algorithm, and we are just analyzing it in a black box manner using this experts framework. Okay, so this is it. And this is our starting static algorithm. Now, why does this work? Why is it a good candidate to dynamize? Now, just to make things specific, I'm going to look at the following setting. We have a covering LP that's undergoing restricting updates, or alternatively, you can think of the dual packing LP is undergoing relaxing updates, and we just want to maintain an epsilon approximate solution. Okay, here is the main insight behind dynamization. Yeah, go ahead.
Can you, what does it mean in the set cover world? You're deleting elements or reducing the.
Okay, good. In the set cover world, it just means, let's say we are inserting elements. That's a restricting update in the set cover world.
Oh, you're inserting a new element.
Yeah, inserting a new element.
And so it's not covered yet.
Yeah. So the existing solution might no longer be valid.
Okay.
Sorry, I thought you were only changing the constraint matrix.
Okay, good.
So it'd be like you are removing an element from a set.
No, okay, if you think in terms of constraint matrix, it will be like, oh, give me 1 second. If you think in terms of entry updates, that would be, you are saying, okay, this element now no longer belongs to this set. That's a restricting update. And you can also think of a restricting update in terms of just inserting a new constraint. That also shrinks the feasible region. So both of these are restricting updates. It just is whichever one you find easier to visualize. We can handle both of them. Okay, so that's the setting. Now, what is the main challenge here? The multiplicative weights update is essentially an iterative algorithm. So what it is doing is it's just running in rounds, just in the static setting. And in each round, it's just checking a condition. And the condition here is basically whether there exists some constraint, some element that is not yet covered. And if this condition holds, then you just whack that constraint, satisfy that constraint, and move on to the next round. Otherwise, if the condition does not hold, that's a cross here with red, then you just return your existing solution. So you keep doing these rounds like this in the static setting, and then at some point you stop. Now, these type of iterative algorithms would usually be very hard to dynamize. Why? Because what is happening in a round very much depends on what happened in the previous round. So if I now just make a small update, maybe in this round you wanted to do something different, and that would have a huge cascading effect going forward. So that's one issue. Now, in our case, the key insight is this. These partially dynamic settings with the restricting updates are nice in the sense that after a restricting update, the past decisions that you have made continue to remain valid. So for instance, if you visualize a restricting update by saying that, okay, an element is being inserted, that's our restricting update. So there was a constraint that's now present, which was not present before. And we are currently here. So in previous round, so let's say in this round, what happened? We just identified a violated constraint, we whacked it. That decision is still valid. It's a still valid round for the current input. So all we need to do is now just move forward. So, okay, maybe after insertion of a new constraint, we are now in this case here. So we just whack that constraint and keep whacking for a few more rounds, and then we get stopped. And we stop here. And eventually, when we reach round T, we can just output the dual packing solution. So that's the high-level insight as to why it works in the partially dynamic setting.
Just one brief clarification. The whacking that you do, it doesn't in one step make sure that the constraint is satisfied, right?
You might need to do multiple whacks.
Yeah. Okay.
And actually clubbing together these whacks is how you get a fast static implementation.
Okay.
Okay. So now let me just give you precisely what the dynamic algorithm would look like in this basic template. And let's just assume that initially, let's say for the set cover instance, there were no elements. So all these constraints were trivially satisfied after our initialization step, where we initialize the weight of every set to 1 and weight of every element to 0. So this is pre-processing. And at this time, we are in round 0. Now, at some point in time, a restricting update comes. What might happen? Maybe there is some new constraint that is violated, which was not violated before. So we will just happily go along and just implement the next round. So in the next round, we are just supposed to increment the dual weight by 1. Did this. We multiplicatively update the weights of the sets. Did that. And then if we have reached this threshold capital T, then we have gone on for too many iterations. So we will just claim that the dual solution we have is a feasible packing solution. So we will just stop doing any computation. We'll just output this Y at all future time steps as a feasible packing solution. And now under restricting updates, if Y is a feasible packing solution now, it remains a feasible packing solution at all future time steps. That's it. So it's as if you are just taking the static algorithm and just seamlessly extending it to the dynamic setting. And you can go through the math, and the key lemma that we proved still works in this setting. Okay. Any question? Okay. So now, as it was pointed out very clearly that right now we are saying that run this for lambda log n rounds. Even in the static setting, this is not very efficient because lambda might be polynomial. We want a near linear time implementation to begin with in the static setting. So here is a standard way of making it near linear time. We are now back in the static setting. So if you look at what this algorithm is doing, what is the inefficient part? So if you just look at one whacking step, this part is actually very fast. All we are saying is, okay, look at one particular constraint I that is violated, provided we manage to find that constraint quickly. Then you just look at all the sets that participate in that constraint. You are just multiplying the weights of those sets. And this takes time proportional to just the number of non-zero coefficients in that constraint. This is fast enough for us. So whacking a single constraint can be done fast. The problem is number of rounds is too large. We can't afford lambda log n many rounds. So how to make this fast? Ideally, we'd like to say something like that. This algorithm would whack every constraint only polylog many times. Then we'll be happy. So what we do, we just slightly modify this algorithm. Yeah.
So I'm confused. Why is it enough that the number of non-zero? Earlier you said you can add an element that's not covered by any sets. Can you have a lot of non-zeros in that case?
Good point. When I say number of non-zeros, it's a partially dynamic setting. So it's look at the final state of the constraint matrix, the number of non-zeros you have at that time. And our total update time will be with respect to that.
But this is when you're amortizing by the number of ones in the matrix, not the number of rows. Because earlier you said you're adding an element.
Oh, okay. So if your question is that, okay, a restricting update just inserts a new constraint which maybe has 1,000 many non-zero coefficients, then of course the time should be proportional to the number of non-zero coefficients you inserted. You can't expect to have polylog time. Yeah.
Thanks.
Okay, good. So ideally we'd like to say something like this, but it's too good to be true, but there is an easy fix. So the easy fix is this. We'll just run this algorithm in phases. And we will just use the fact that these weights are monotonically increasing. So the weights on the sets are increasing monotonically. So we initiate a new phase whenever the sum of the weights on the sets increases by a multiplicative 1 plus epsilon factor. And now this is an easy claim to prove. I will just skip this proof because of lack of time. We can show that the total weights on the sets will remain polynomially bounded. And once you have this, it just immediately implies that the number of phases would just be log n, because you are initiating a phase only when this total weight increases by 1 plus epsilon factor, and initially the total weight was just n. Now what we do in one phase, let capital W denote the total weights of the sets at the start of the phase. This will remain fixed. Capital W, the value of capital W remains fixed. And throughout the phase, I will just pretend that the actual value of the variable xj is just its weight divided by capital W, not the actual sum of total weights. And this is fine because capital W is at most a multiplicative 1 plus epsilon factor off from the sum of total weights. So nothing should change as far as approximation guarantee is concerned. And now in this phase, what we are doing is we are just looping through all the constraints one at a time. And whenever we reach constraint I, we just keep whacking it until it gets satisfied. That's how we club together all the whacks. And now here is the crucial observation. For the rest of the phase, once we are done with this, this constraint will remain satisfied. Why? Because capital W did not change and xj hat only increases. So within the phase, the value of xj can only go up. So if right now this constraint is satisfied, it's a covering constraint. Let's look at this constraint. It's satisfied right now. In future, xj values can only go up. So this covering constraint will continue to remain satisfied. And now this step, keep whacking I until it gets satisfied, can be done in near linear time in the size of the constraint. And that why? Because you first guess the number of times you need to whack this constraint to satisfy this, and this is a simple binary search. And once you have figured out this value, you just go ahead and do this for every variable appearing in this constraint. So one iteration of these for loops just takes near linear time in the size of the concerned constraint, and you are going to consider a constraint at most once during this for loop. So the time taken to implement a phase is just near linear in the number of non-zero entries in the entire constraint matrix. And there are only log n many phases, so the total time over all phases is also log n. So this is how you implement it in near linear time. And now you go ahead and say that, okay, what happens in the dynamic setting? Okay, you need to prove this claim, which I will skip. And now you ask what happens in the dynamic setting. You can just come up with a very natural generalization of the scheme I presented right now that works. But there is one additional challenge. The challenge just is, I'll just point out the challenge and skip the proof as to how we overcome this challenge. So the dynamic variant of this scheme would be that we are in the current phase. A restricting update arrives. We identify this constraint that is violated. Keep whacking I until it gets satisfied. Fine. But in the static setting, the analysis crucially hinged on the fact that this constraint will remain satisfied throughout the rest of the phase. This is no longer true in the dynamic setting, because maybe you whack this constraint sufficiently to satisfy it. In future, there might be one other restricting update, which is basically reducing the value of some Cij, and it becomes violated again. So that's a problem that we need to address. But with some extra work, it no longer holds under restricting updates. So what we say is, let's just look at this operation, keep whacking I until it gets satisfied. I'll just call this operation enforcing a constraint I, enforcement of constraint I. With some extra work, we can prove this key lemma that in the dynamic setting, a given constraint I would get enforced at most polylog times. This is slightly non-trivial, but it holds. And so now I skip the proof of the key lemma. Okay. And that's it. So now to conclude, I'll just conclude with, I think, two main open questions. One is we could extend our framework to mixed packing covering LPs, however, only under relaxing updates. And for technical reasons, we could not solve mixed packing covering LPs under restricting updates. And there is every reason to believe that such an algorithm might exist. That's one open question. And the second thing is, this is the question that I started with, that in static approximation algorithms, there are so many instances where you first solve it in relaxation and then round it. Now that we know how to solve packing covering LPs, can we do this, apply this framework for other dynamic problems? And here, one other challenge we might need to overcome is what Omri pointed out, that we are just assuming explicit LPs. So in many natural problems, the LP might have exponentially many constraints, and we need to deal with that. So that's it. Thank you.
Yeah, I had a question about the lower bound you proved fully dynamic.
Yeah.
Um,
Oh, let me see if I can go to.
so the lower bound for the fully dynamic,
Yeah.
for fully dynamic.
I'll just go there. Just give me.
Yeah. Yeah. So what kind of updates does it assume? Does it assume element insertions and deletions, or
No. It's
the entry?
Yeah, it's the weakest form of update you can assume. So it's basically changing one entry of the constraint matrix.
I see. And does it also imply anything for set cover?
No, it doesn't imply anything for set.
Oh, okay.
One other direction for generalization is going beyond LPs. And so one, I don't know if there's work on this, but can one dynamically maintain a solution to max cut, for example, which uses a semi-definite program?
That's an excellent question. I don't know, but I do agree that's an excellent open question. Let me check it.
I was wondering how the speed up of your algorithm, the part where like binary search for the number of times the whack-a-mole, compared to like with an independent multiplied update.
So I just said this. If we just think of epsilon dependencies, if you just look at the static algorithm we have, okay, I shouldn't say we have. This was known in the literature already. When we go from the static to dynamic setting, we don't incur any extra epsilon factor loss. So I don't know if there is any alternate variant of the static algorithm which incurs less epsilon factor loss. That I don't know.
So I thought with independent multiplied update also gives you like 1 over epsilon squared. Right?
1 over?
1 over epsilon squared.
Oh, so here's the thing. Let me just point this thing out. When I wrote this thing 1 over epsilon cubed, if you just look at this problem precisely in this slide, for this our amortized update time is 1 over epsilon squared. Now, why I'm writing 1 over epsilon cubed here? Because when you just throw in an objective function in the partially dynamic setting, you need to make guesses on the objective function. That incurs an extra epsilon factor.
So there is a linear over epsilon packing algorithm. It's just not there to dynamize.
Yeah, right. That's true. I don't know how to dynamize it.
One quick question. So can we hope for de-amortization of the algorithm?
The lower bound here says that even worst case update time is not possible.
Oh, even like the weak, the result number one, like the
Even under partially dynamic updates. And basically, this lower bound is not that difficult once you just identify the starting conjecture to reduce it from. And this is actually quite standard in dynamic algorithms, that you get a fully dynamic an amortized lower bound in the fully dynamic world. And simultaneously, that gives you a worst case lower bound in the partially dynamic world. And that's precisely what's happening here.
Thank you. Are there other questions or comments? Maybe I have one more question. I think you have applications in your paper, right? And I would be interested in, like, you know, maybe just repeat these applications maybe a bit. I would also be interested in, can you reconstruct any known results? Maybe not, you know, up to like the best known bound, but
good.
Morally.
So on this note, I'll just say we can reconstruct what Aaron presented in the morning. Because let's say decremental matching, even weighted matching, if you ignore exact polylog n dependencies or exact 1 over epsilon dependencies, decremental matching is a case of maintaining a packing LP under restricting updates. So now I actually don't have a very good intuition myself as to, is this multiplicative weight update thing doing the same thing as congestion balancing or not? I don't know. But yeah, so you can get decremental matching using multiplicative weight updates.
Okay, thanks, Simon. Okay, then there's a break now. Let's thank Sayan again, and we meet again at 3:15.
Thank you.